Hello, everyone. Good afternoon. Thanks for joining us. And I think seminar number 5 now for the spring semester here. We're very excited to have Dr. Rich Signell from the USGS in Woods Hole. Rich received his PhD in physical oceanography from the MIT Woods Hole Joint Program in 1989 and joined the USGS immediately thereafter. He says it's his dream job, basically, and we're absolutely pleased to have him here to talk about improving the interoperability of Earth Sciences data collection. So without further ado.
All right, thanks, Kevin. Well, I'm really thrilled that all you guys came out today with this kind of title. It's not a science talk really. But it's about enabling science. And my dad taught physics at Michigan State, and he, when I was doing numerical modeling, he invited me out to give a physics colloquium in the physics department. And afterwards, one of the guys came up and he said, that was interesting. It wasn't physics, but it was interesting. So I hope that everyone here finds something interesting in this presentation, and hopefully more than interesting, hopefully something useful you can actually take back and enable you to do more efficient science by using better tools. All right, I hope you see some of these tools that you may find interesting. And actually, I wanted to, does this picture look familiar? I've been seeing it all day here in the building, except that this is a little bit different, actually. This is the forecast currents right now. This is from the New England forecast model that's running as part of the Integrated Ocean Observing System, an unstructured grid, triangle-based model, FVCOM, and this is showing the ebb currents on the ebb currents in Boston Harbor. And what's notable about this, I think, is that, this could have just been an image that I grabbed off a web page, and it is actually. I actually stopped at a Dunkin' Donuts and fired up my laptop and connected to the web, but it's actually in an IPython notebook. Which means, so if I could show you the rest of this, there's actually code up here that makes this plot. And I can enter the code into the web browser, and it produces the plot below the cell of code that I just executed. And so this kind of, so I have the data here, I guess is what I'm trying to say, not just the picture. And I can do any kind of analysis I want through my web browser using Python, which is very Matlab-like, and access data remotely. In this case, I've just grabbed, obviously, a little snapshot of velocity data out of a file that's several gigabytes. And we have actually, there's a 30-year hindcast, which I'll talk about later, which is 33 terabytes.
Rich, we should say that Massimo will be here in a couple of weeks to give a seminar. So.
Yeah, that's right. And Massimo is the guy who turned us on to this IPython notebook. There's an incredible amount of development here. And when Massimo comes, you'll see really the real power of the notebook to integrate across different kinds of languages like Matlab and R and Python, and do it all in a rich text context where you can include math and everything. So it's a really exciting thing for education, and I think it's really an exciting thing for scientific workflow, capturing scientific workflows and sharing them with other people, open science, repeatable science, and shareable. Anyway, Massimo, I'm not going to steal his thunder by spending any more time talking about the IPython notebook, but he's really the guru, and he's actually a really integral part of the development team. So when is that? That's like in
A couple weeks.
couple weeks?
Next week.
Kevin, next week?
I think it's probably 2 weeks.
We'll figure it out.
I think he's in Norway. Anyway, okay, so you might have noticed that this has an integrated ocean observing system background here. And I actually, a lot of this stuff that I'm going to be talking about, I started when I did a detail to the NOAA IUS program. So I'm at the USGS permanently, but I did a 1-year detail to the Integrated Ocean Observing System to help them on this issue of model interoperability. And what I mean by that, well, they had so this is, just for a little background on IUS, there's 11 different regions in IUS, and up here in the Northeast, it's the Syracuse region. And what the concept behind IUS is that the federal government is not going to be making all the relevant observations in a particular region to to actually solve problems that are very usually regional in nature. And there's a lot of other folks making measurements and doing modeling in these in every region, from state and a local government to academic institutions. And so how could you actually try to take all those pieces and make sort of something more out of it? And so in all these different regions, there's all sorts of different kinds of measurements being made, and also all kinds of different models being run. Okay, so they wanted to have a way of trying to compare different model results in different regions, and this is sort of what we had before, actually, and this is even before IUSE. This is the thing that really got me going on this. So I was doing numerical modeling in the Gulf of Maine, and I would see these different modeling products, and this was produced by, this is way back in 2008. So this was coming from the University of Maine. They had a web page you could click on and look at the velocities. And then UMass Boston actually had a forecast model for Massachusetts Bay. And it'd be kind of nice to be able to compare these, right? And not just sit here and look at the picture and go, geez, this is a different color scale. I mean, this is the surface temperature on the same day, right? So, and in both of them, it was hard to get the data. It was just a big pain in the neck. And if you have model data just trapped in the hands of the modelers, and observationalists and other people in the field can't get to it very easily, that's just not a very good situation. So IUSE. Now, so IUSE has this data management component to it, and basically what they're trying to promote is all the data that flows through IUSE, whether it's from observations or models, goes through some kind of web service. And so it's not about files as much as it is providing services that can get then consumed as files or integrated directly into programs, on the downstream side. And they're trying to use standards that have been developed by the GIS community, the Open Geospatial Consortium, or ISO, or the NSF-funded Unidata operation out of UCAR. Okay, so what does this mean? Now I'm going to basically just give a one-slide overview of what a netcdf file is. So, in the beginning, right, when we were writing model output, we were writing ASCII files, we were writing machine-specific binary files, and and 25 years ago, Unidata came up with a netcdf file. And a netcdf file is really pretty simple, but it's a machine independent. I mean, you can take it from one machine to another. You know how big the variables are. Okay, you know what type of variables there are. And you can write multi-dimensional data into this is just a topography data set, eTopo2. So you have here longitude, latitude, a short variable called topo, which is, of course, is the elevation, and it has units in this case, and it has a missing value and a little bit of attribute information down here. But you know how big it is, you know what type of data it is, so you can take this from machine to machine, and you can dip into it and pull out. They wrote a library that allows you to dip in and pull little pieces out of it very efficiently. So even though the files can be big, you can dip in and pull out just the time step or the variable that you want. So that's 25 years ago. And it's catching on in the oceanographic community. Took a while. And then along with this really came the thing OpenDAP. And this is now a service then that can, I think the easiest way to think about this, or the way I always think about it, is it's like you can access a netcdf file, but the netcdf file doesn't have to be on your machine. So it can be somewhere, there's a data set somewhere else sitting on a machine, and if you provide this OpenDAP service, you can actually enter a URL like this, some big long thing, and then the variable you want, and then you can subset out some indices of that variable. So again, this allows you to dip into a data set and pull out just the chunk you want, but now the file doesn't have to be local. And there's lots of different applications that can consume OpenDAP, Matlab, Python, R, ArcGIS. There's actually just a whole ton of them, because this has been around for quite a while too. So this is kind of like the de facto community standard service that climate folks and ocean folks and many Met folks use. So in the coastal ocean, we have a little issue, because unlike bathymetry, where we often have a uniform grid at the end of the day. Our models in the coastal ocean have these curvilinear horizontal coordinates, so there's smaller grid cells over here than over here near this open boundary. This is a Massa Bay model. And then there's this sort of, this fence here is representing the vertical distribution of levels, which are, as you can tell, there's 20, or I don't know, 14 levels here. And they track there's 14 levels where it's shallow, there's 14 levels where it's deep. So this is going up and down with the sea surface. So the Z coordinate, this is the Z data. If you want to grab some temperature data at a particular time step, you have to calculate the Z positions of all those data values that come back by knowing where the sea surface is and by applying some equation. Well, that's like, geez, how are we going to standardize that? Well, this group came along, the Climate and Forecast Conventions group, which came out of the climate community, and developed a bunch of conventions for how to specify those kind of complicated vertical coordinates where things are going up and down, and the curvilinear coordinates. It's basically saying, okay, if the user wants to read temperature or salinity, how do I find X, Y, Z, and T? How can I pull that out of the file in a way that the user doesn't have to know something more and be looking through the file and trying to figure it out? So the CF metadata is great, except there's no guarantee that people are going to do it, or are going to write that kind of output. And in fact, when we went around and looked at all the different kind of models, so this is a interoperability diagram. This is basically the design plan that we came up with to do this interoperability bit. And so we had over on the left a whole bunch of different model outputs from all these different models. And they all wrote netcdf files. And they were all non-CF compliant. And so we could have gone back to the model producers and said, hey guys, you got to change all your output, make it CF compliant, and when you do that, then then we can hook you up. But luckily, Unidata, they have this Threads data server, which is sort of everything inside this little box here, essentially, and it's composed of a common data model, okay, which is really those CF conventions applied. So this common data model can represent all of these different data, all these different model outputs, whether they're a sigma coordinate or double sigma or a sigma over Z, or they're curvilinear or rectilinear, but needs those CF conventions. So instead of saying, okay, you guys have to write your files over, there's this little bit of XML in here that allows you, someone who knows the CF convention, to say, you know what, I'm just going to add the little attributes into that netcdf. I'm going to add the attributes to that data set without forcing these guys to rewrite the data. So it's basically putting a little metadata on top of whatever the model producers provided. And that was huge, because now they didn't have to change their output. And when they don't have to change their output, that means like their existing applications aren't going to break. And so really it's no pain for them. You can just say, hey, just leave your files the way they are, that's fine. And somebody who knows the standard can apply this little bit of XML, and it doesn't change. Every ROM's model output is pretty much the same with the ECOM and WRF, POM. And so they can all be fed through this common data model. And once you've got everything in a common model, then it can go out through a whole bunch of different services. So here's the OpenDAP with CF conventions here, and WCS, a web coverage service which delivers data. It's an OGC service. Are people familiar with it? Is this all like totally, have you heard of WMS before? Yeah, a few people. Okay, so anyway, so it goes out through this service, and then you can attach a whole bunch of different clients or applications over here on the right. So, so you have all sorts of clients over here, you have all sorts of model output over here, and by going through a common data model, so maybe you have N of these, N different models and M different clients over here. If you tried to just connect up all these models to all these different clients, you have an N times M number of connections, right? And if you do it this way, you have M plus N. And maybe it doesn't matter if there's only 3 of these, but if there's 15 of these and 15 of these, that's a big deal. So you definitely want to go through this common data model kind of approach. And not only just for model output, but really for anything. I mean, a lot of you probably are familiar with the GDAL package, that converts different raster formats to other raster formats. That's a common data model for raster data internally. So you can read in all sorts of stuff on one end and put out all sorts of stuff on the other end, because that has an internal common data model for raster data. And just in passing, this has been so successful that Unidata has come up with a common data model for time series, for point data, for profiles, for trajectories, and swaths, and collections of time series and collections of profiles. And so, I think in oceanography, in the geosciences, if your data fits any of those kind of models, we're going to have like a countable number, maybe 10 or 12, maybe not as quite as many common data models that we can use to put all sorts of weird type of sensor data and gridded data here, go through common data models and out through services to the clients. Okay, so I just want to actually mention one little extra piece here is that, one other, there's a NetCDF subset service for people who just want to get NetCDF files. So they can go to a GUI and enter in what variable they want and the range and time and everything and get a NetCDF file. There's also this NC ISO service. This was actually added into this by some folks at NOAA who basically said, okay, if you put certain attributes in these files here or in this layer here, like metadata, it can come out as ISO metadata as a service. So this is a metadata service. Then so like usually scientists, you talk to them about metadata, they're like, you're going to want me to enter some metadata form, only if they, have to because they're not going to get their funding or something. But if you tell them like, okay, you work in Matlab, here's just some, here's like a little bit of extra stuff you can toss into your NetCDF file, and it'll come out as ISO on the end, and satisfy some requirement. That's a lot more palatable to people. So once it comes out as ISO metadata, it can be consumed by these other things. And I'm going to talk about actually that a little bit later, because that's pretty cool. That's how you get to search. All right, so what can you do once you've got your data through there? One thing you can do is look at it. There's through that WMS service, the web map service. Actually, on the Threads data server page, if you click at the bottom, there's a link to a client, an application, a web client called Godiva, which is being shown here, which consumes the WMS service that Threads provides. So here actually is the current forecast temperature from a model that we're running at the USGS. John Warner is running that actually has this three-dimensional model with temperature, salinity, and sediment in it. It's a fully coupled wave, ocean, and atmospheric model. And you can click over here on the calendar, and you can actually click a first frame and a last frame and make a little animation, and click on a point and do a time series. So you can do kind of browse like stuff right out of the box. And by the way, this was developed by folks over at the Reading eScience Center in the UK. So they built this, and now it became part of this. So the Unidata folks have contributed some, the NOAA folks have contributed some. Now the Reading eScience Center provided this nice little WMS service that was added in. So Unidata didn't actually build this, they just added it in to the server as an additional service. So you can browse the data, but as I said before, and if you want to look in 3D, you can actually use, here's an example of a tool that the Unidata IDV, which is a free Java application, you can download, and you can connect to these different CF-compliant data sets. And this is actually showing an ISO service of salinity entering the Gulf of Maine in a 3D view draped over some bottom temperatures, and then some streamlines from another data set from WRF. So you can integrate, you can pull met data, ocean data, wave data into the same environment, and if they're all CF compliant, you don't have to know anything about those different models. You just give it the URL, you pick the variable you want, you add it to the display. This is a fully 3D, you can rotate stuff around, you can animate through time and stuff. Okay, but this is still looking at data. And actually, I really was sick of looking at data. I wanted to get the data. And so we built a toolbox from Matlab, which is actually, it's now called NC Toolbox, and it's on GitHub. And it allows you to take advantage of all this common data model stuff. So you can do things like give it a URL and a variable name and a time step, and it will return to you the data here in T. So here's a three-dimensional data chunk, 22 layers by 120 by 180. That's 22 levels by lat by lawn, and then this geo thing that gets returned comes back and it has the latitudes, longitudes, all the z-values, three-dimensional z-values, and a time stamp that is the Matlab time. So no more like trying to figure out, what the time is from the .cdf file, and and then figure out, okay, which are the latitude and latitude. Oh, geez, now we got a sigma coordinate. How do we convert that? Blah blah blah. This all happens automatically because you have CF compliant data, and you don't need to know anything about that particular model, only that it was CF compliant. So so this works, like I said, okay, it works for any of these models, and this URL can actually be a local netcdf file, a remote netcdf file. It can be one of these NCML things, or it can be this open DAP. This is the way we almost always use it. And this is really transformed in our group, in our modeling group. This has really transformed the way that we do the science that we do now. We don't actually bring any data back to our local machines. We just leave it all sitting on our file server, and we access it through OpenDAP. And this means that when we write MATLAB code, we can share it with anybody in the group, and it works just the same. We can share it with a collaborator, and it works just the same. You can fire it up in your hotel room, and it works just the same. No changing file paths and stuff like that. Okay, and so this is the payoff. You can then go grab some data from that model A, the UMass model, the main model, and oh, by the way, I can go grab some data from Coastwatch, and using the exact same command, and compare those surface temperatures on the same color scale. Because I have the data, I can make the color scale. And in this case, well, there's something going on here that we maybe should investigate. So actually, and almost every time you start doing this, you start poking your nose around in model output, you start finding things. And that's a good thing. You get back to the model, and model's like, whoa, I didn't know that was happening. And and we spiral upward. And this is actually another function in the toolbox that you guys might find interesting. If you can, this is a virtual glider path, this little gen slice. So here was a Rutgers glider that was traveling back and forth across the shelf off the Delaware. And so there's the data. And with this little tool, you just point it at a URL and you give it the glider path, and it comes back and it gives you the vertical, the equivalent as seen it from the model. So here's the the model glider path, and then this is from the this is actually from the NCOM global model, and this at the time was the HICOM global model. And unfortunately, in HICOM, and they still do this, this actually was a stretched vertical coordinate model, but they interpolated everything onto standard levels because it's easier for people to deal with. So it just goes, give me a z value. But that's removing a lot of scientific content from the model. And so we're really trying to fight the, dumb it down early so that people can access it in the same kind of, in an easy way, and say, look, if you use this kind of common data model approach, you can keep the original native grid information from the models, which is the way to preserve the most amount of scientific information. That's the right way. And this is just showing you can dip in and pull time series out of these model things. So here I'm showing a wave height from a buoy on the Great Lakes. So actually, what I did in this year is that I actually went around either physically or virtually to all these 11 organizations in IUS, and I helped set up that thread server, that threads data server, and help them create the little NCML bits. And then they were good to go. And I'd usually come in, I give a talk like this. We go have some, I'd sit down with their tech folks right after and figure out what they needed to, look at their data and help get this, go out and have a beer, come back the next morning, and get the thing running, and leave them with a functioning server that was serving their own data in a new way. And it was really a lot of fun, and it was really rewarding and successful. So I want to keep doing that. And this is just showing, it's not just model output. And here's grabbing some NAM data from a this was a nice front. Actually, I didn't know there was a 4-kilometer NAM model running in this region. And it really makes, when the fronts move through, it really looks nice on a 4-kilometer grid. So this is a little Matlab routine, get NAM now or something like that. But again, it's just accessing CF compliant data. And then in Deepwater Horizon, this was really handy because there were a whole bunch of people running all sorts of different models down there. And this provided a way where, again, we could compare all these different models, by pulling in the data. We worked with those folks to make it CF compliant again. And Fukushima, actually, the Navy, there was a ship actually out, a Hui ship that was out actually trying to figure out where the radiation was going to go shortly after, and they wanted to use these model results. And the output from this model, the Navy quickly spun up this NCOM 1 kilometer model. But the output was in like 9 gigabyte tar GZ'd netcdf files on an FTP site. So these guys on the ship, they're not gonna get that, right? So we unpacked the data, threw it onto a thread server, and then they were able to extract. This is just showing, temperature. This is actually showing current speed. But they were able to then just grab the surface layer of velocities that they needed for the next 2 days to predict where what they were seeing in the water was going to go in a couple of days. So they were able to just grab a few hundred K out of that massive data set. So it's really, really, really useful. So is it all just Matlab? As I mentioned before, this IPython notebook is pretty cool, and the British Met Office has developed a Python sort of equivalent of what I was just talking about from Matlab. So if you look for Iris, if you're a Python person, you find this library which does nice things if you use the CF data model. And they're going great guns on this right now. So this is actually showing using this Python tool to grab, so two weekends ago, I found out there was a 30-year hindcast of waves, actually for the global ocean, but with higher resolution along the coast. And I thought, well, it'd be kind of neat to grab that, and look at what's happening on the East Coast here. So this is 30 years of climate, CFSR, the climate forecast, whatever it's called. John, you wait back there. Do you know what this thing is? The CFSR, I forget what that stands for, but anyway, it's a climate forecast, I don't know. Anyway, it's a reanalysis product that
it's like the Tencent reanalysis.
Yeah, it's
Is
a
it the global version of it, or?
right, and it's a sort of an update of the previous NAR, the NAR. We used to have the NAR, North American Regional whatever reanalysis. This is a global one. Anyway, it was used to drive this wave model, Wave Watch 3, with higher resolution along the coast. And again, there was to get this data though, it was 6,000 GRIB2 files on an FTP site. So start the little thing running, grab all the files, and stick them up on our thread server. And with just a few lines of code, we can combine this all into just one URL. So you can go in here, and using this Iris toolbox in Python here, you can see you load up this URL, okay, and you've got this thing called cubes. You say print cubes, and it prints out the variables you have, and again, the latitude, blah, blah, the size. Okay, here I'm going to say, I want the significant wave height. So I'm going to take cube 0, and I'm going to do this slice. I'm going to extract, I want to find this time step, and I'm going to find it in this range. And notice there's nothing about where the latitude and longitude variable is or any of that stuff. Again, because it's CF compliant, it'll just find it and plot it up. And here is the wave height for May 7th, 1989. So you can go back and look at the perfect storm, check it out. I should have done that actually. That would have been nice. Okay, and then you already saw this one. But this is just showing, of course, again, you can access unstructured grid. Oh, I know. I put this in here because the unstructured grid stuff is actually not, we don't really have a common data model library for this. We do have a standard now that we've been working on with all the different unstructured grid modeling folks, but we don't have a model, we don't have a library that really takes advantage of it. So we're working on it, but that doesn't mean, just because we don't have a library that can take advantage of it, doesn't mean you can't just grab the data through OpenDAP and plot it up, and that's what I've done here. But I had to know which variable was latitude. I had to go look and say, oh, well, that's latitude, and that's longitude, and oh, this thing over here, that's the thing that connects all the triangles together and tells me what nodes are in what triangle. Okay, well, it's not that hard to do. Okay, and Arc. What about Arc? How many people use ArcGIS? A few, yeah. So this was for me as a modeler, this was people would go like, can you give me that model output in Arc? And I'd be like, I don't know how to do that. And so when Python came along, though, as an interface to Arc, I suddenly got kind of interested, because now you can import this netcdf4 like module, and it gives you OpenDAP access. So even though it says netcdf4 here, what I'm opening is an OpenDAP URL. So I can open that same URL in ArcPy and load in that data. So I'm bringing in some topography data. I've clipped out a little piece of topography data and brought it in using this ArcPy NumPy array to raster routine. Woohoo! And here it is. So that's awesome. But what about model output? Well, you can do the same thing with model output. There's no, the common data model stuff will help you for structured grids. For unstructured grids, you still, like I'm saying, you have to read the variables, but you can still use this Python interface and bring the data in. And this is the case I brought in this shapefile, but the really cool thing was with this unstructured grid, was as I previously mentioned, so here's a grid, a model output that was brought in as a tin. Triangulated I don't know what it is. What is it?
Triangular, irregular
network.
Triangulated irregular network?
Yeah, triangulated irregular network. And so you can do this import netcdf, import ArcPy, open this thing up, and then you use this crazy land XML to, you have to write out the data as land XML and then read it in. But the point is, though, this is you can get the model output on the native grid again into Arc, and you can just pull in the piece you want. So the state of Massachusetts, which contracted UMass Dartmouth to run a 30-year hindcast of 3D circulation in water properties in the Gulf of Maine, ended up with this 33 terabyte data set, and the money was pretty much gone, and they were kind of starting to freak out a little bit, like, what products do we ask for? What are we going to do with it? And do we need like standard deviation of temperature, like per month, or maybe the means, let's see, the monthly means, and we want the seasonal means. Oh, geez, maybe just surface and I don't know. And it's tough, right? You can't anticipate all the possible, things that you might want to need for making environmental management decisions. So instead, though, we can give them some tools now where they can actually create their own products, right? If they want to go look at a particular bottom stress on a particular day at the full resolution, they can do it. They can use this tool, and they can grab it, and they can go in, zoom in, and when they get into Boston Harbor, and they've got this funny tin, and they're like, I don't know, I really know what a tin is, they can convert it to a raster in Arc. So they've got the original grid data, but they can convert it to a raster, and since they've got it as a raster, they can do all the stuff they know how to do with rasters, and they've got all, they can make it as high resolution as they want, which they couldn't do before, because then instead of 33 terabytes, it would have been, I don't know what, huge and huger. And so they can do all the neat stuff that they want to do on raster, but only at the resolution, at the resolution that they control, not that they had to decide from the beginning. So basically putting tools in the hands of the folks who want to make the decisions so they can create their own products. Okay? So one more thing that is pretty cool that we were able to do with this was, since they were running this thing, actually it took 2 years to run, 2 years of wall clock to run this 33-year simulation. So it was chunking away, and some of us had been tapped to be on the model steering committee, something like that. And we were supposed to be helping them figure out if this stuff was any good as it was running along. So we instead of waiting after 2 years and looking at it going, oh, geez, no, you better change some parameters and run it again. We thought, okay, let's start looking at it as the model was running, like after a couple of years. It started in 1979. Well, actually, we had some measurements out in the Gulf of Maine in 1979. Actually, quite a bit of measurements in those years where Georges Bank was being studied pretty extensively. USGS had a lot of data. Hui had a lot of data. Fisheries had a lot of data. Yeah, well, that sounded kind of like a big job to actually try to do that. So we thought, well, maybe we can use this stuff to make that job simpler. So we had 6,000 different time series in 3 different thread servers. So we were serving our time series through the same thing. So we had all these USGS, NOAA, and Hui data sets. And if you remember this part right here, where I was saying you could grab the metadata and then use these tools over here to search. We use this one GI-cat, which is another little simple thing you can just drop on a server. And this is their diagram for GI-cat. This is an Italian group that's generating this, Stefano Nativi and company over at the CNR, their national research agency. And now, I'm sorry, but this is backwards in a sense, because this is all the data types that they can consume, they can grab metadata from. So they have ones, they can grab metadata not only from threads, but from things like, NetCF files, GeoRSS, whatever that is, GBIF, which is biological diversity, I think, or something. And then all these different OGC services. They can harvest metadata from these different services, bring them into, now this common data model is the ISO metadata model. They stick them in a database, and then you can query that database by using any of these services here. So OpenSearch, a simple one, CSW, this is a catalog services for the web service. Okay, so God, what the hell is all this stuff? Okay, so what this allows you to do then is you set up this GI, you point it at these 3 threads catalogs, it pulls in all that metadata, sticks it in a database, and then you can just do, in Matlab, we have a little simple thing that's part of that NC toolbox called OpenSearch. You probably can't read that, but so you point it at, so here's a little workflow. This is a scientific workflow that we're going to use to assess how well this model is doing. We open up this data set, which is the 33 terabyte file of hourly data, right? We find out the extents of that data, the latitude and longitude extents. We look for, and then we want to look for seawater velocity in our data files. We construct this query that's looking in, it can either look in the model extent or it can look in a particular extent that we specify, and it's going to use the time range from this model. And then it's going to do the search, and it's going to return to us all those data access links, all those OpenDAP links that it found that met these criteria. So it's going to find all the velocity data in all those different catalogs that meet these criteria. And then we can start ripping through all these data sets and comparing the data to the model automatically, right? This is like a 120-line script. Goes in and does this, and it computes. So it computes for every time series it finds. It computes a model time series by interpolating, getting that same information. And then we do things like tidal analysis. This is a plot of the M2 amplitude, one versus the other, data and model. That's looking pretty good. We can plot up the mean flows. Here's the mean from the data over on Georges Bank. So like I said, a lot of the early data was from Georges Bank. Here's some inflow in the Southeast Channel and some, outflow on the model. Okay, so we have some things to look at, right? So, but the main point of this was that we turned what would probably be like a year of grad student time or something into, a script that we could just hand off to these guys at UMass and they could run it. And as the model ran, another month went by, and it had done another year of data, of model output. Just run it again, picks up some more time series, plots them up. Because you have the data in your hands. And it also created a little KML at the end with a little thing, a little URL there you can click on and then get a time series comparison. These are so this is all part of that NC Toolbox stuff. So if you go get NC Toolbox, look in the demos directory, play around in there. Okay, so one more thing you can do. This is really cool. I think some of you might want to do this. Once you've got the data in these big, massive gridded data in CF compliant format, you can start building really other cool tools. This is one that the guys in USGS, the CETA groups, Center for Integrated Data and Analytics, I think. Nate Booth and company in Wisconsin, they created this really cool application where you go in on your web browser. You can select from a bunch of shapefiles that already have been uploaded, or you can upload your own shapefile, or you can just draw on the map and create some region. And I don't think I have all the steps in here, but basically, once you've done that, you select, you get a big list of gridded data sets. And these are things like the last 100 years of precipitation and temperature data on a 4-kilometer grid for the US, or the different climate model projections from like 20 different models with all the different scenarios that you can then use. And what happens is you have one of those big gridded time series data sets, right, that you point this thing at. And what it does is then it goes off and it calculates statistics in the region that you've specified, which could be, Virginia, or it could be your county up here in New Hampshire, if you were curious to see what the climate record looked like in terms of, say, maximum rainfall in your region, or maybe the average rainfall. And so what comes back, and this is, so this is actually showing just an example that I was doing as a dust bowl. This is for some kids, but where I went in and used this tool to grab the historical precipitation data for Texas County, Oklahoma, and see, oh yes, well, there is the Dust Bowl, low precipitation. And also here's the big Texas drought of the 50s. This is data, the red is data. And then, so let's see what these different climate scenarios suggest. And you can just point the thing at these other big data sets, and it'll go off and do the crunching. So this is the average precipitation from these two different scenarios. A1FI is the sort of business as usual scenario, and B1 is the green scenario. And the first thing actually I did is I looked and wanted to see how do all these climate models do, like with the historical record, when you get down to this scale. And the answer is pretty bad. And actually, and I was like, well, does this mean that, what does this mean? Like, and then I talked to the climate people, and they're like, oh, you can't do that. You can't expect a climate model to work on the scale of a county. I'm like, okay, well then what can you do? And they're like, well, maybe you could look at the statistics over a larger region. And it was pretty interesting, actually. Anyway, but it was pretty neat to have this tool where I could actually just kind of do this kind of thing. And you can use it to say, now, you could go back and, like, if you wanted to find the maximum wave height from that 30-year hindcast in the Gulf of Maine, you could, like, lasso the Cape Cod Bay. And then what you get back as a spreadsheet, if you use the web interface, there's also a Python and a Matlab interface where I've actually bypassed the GUI altogether and have just done it, in a program. So here I'm uploading a shapefile, so that's pretty cool. So is this stuff hard? No, as I told you before, it's really easy. And to get this stuff going, because this stuff is all Java based, and all you need to do is you go to some site and you say, do you guys have Java? And they say, yes. And you say, is it Sun Java? And they're like, yeah, let me check. And then if it is, you make sure they have Sun Java. And if they do, then you can you drop this Tomcat thing on there. There's no configure, there's no you don't have to make anything or worry about compiler. And so this takes maybe 15 minutes. Then you bring down the threads data server, and that takes another 15 minutes. You dump a whole bunch of files in a directory, and make a little catalog, and that maybe takes 15 minutes. And basically, you can do this in about an hour. So if anybody wants to set up one of these, I will help you and prove that we can do it in about an hour. And in fact, I did this with Damian Brady from the University of Maine just a month ago or so. And so we did it. We did do it in an hour. And he came up with his little Chesapeake Bay. He had. So this is the results of a water quality model. So of course it doesn't have to be physical variables. So he was pretty excited because for the first time he was able to well, no, he wasn't excited about this. But when you click on one of these things, like if you click on this Godiva 2 link, at the bottom of this page here that we made, that gets automatically made. Then he could do the same little browsing of his, in this case, dissolved organic nitrogen, and you can actually download. He was kind of interested in this. You can select a variable and then click as point data. You can just select you put in a latitude and longitude in one vertical level, and it'll output a spreadsheet. So CSV or NetCDF. And that's kind of neat for a lot of his colleagues. They just wanted to get Excel data. It looks like that. And you can put it into this IDV tool, look at it in 3D, and you could access it in Matlab, and you could access the three-dimensional data as an isosurface of phytoplankton, and you can access it in Python. So, this common data model stuff, I think there's not that much, we can make a lot of progress with just some really simple things. And common data models, this common data model is huge. It's a really important part of trying to make interoperability among all kinds of data in oceanography and in the geosciences, not just structured, grids. But so this stuff is coming along. I think this is dead. Okay. But having these web services, so standard web services now, once you've got the common data model, when you access the data through services, you know what you're going to get. So the client can do nice things with the results. So we need, but if you have tools that are using weird, custom data sets, think about what it would take to just turn them into a tool that can access these common data model data sets instead. Now there are a few things that really need to be done that really should be done on the server side. I've been talking mostly about accessing data and doing stuff on the client, but some things like that virtual glider path through the ocean, that's a lot of data actually to download just to find your little path that ends up being a few hundred K of data at the end of the day. So that script, when I ran it looked cool. It took 45 minutes to run. And I could deal with that because I really wanted the output. But if it was done on the server side, where it was local to the data, it'd be much faster. So some things like that, we really just want a service that, common things like that, we just want to be able to give it a URL and the glider path and give me back the data, or the model data. And
So that might work again.
yeah, I think it'll. Oh, okay. And so it's really easy to set up some of these things to get these services going. And what you get, well, you get a lot of different types of choices for data access. As all the stuff that I mentioned. As a model provider, this was really nice for me because instead of responding to all these custom model output requests from all sorts of people, I could just sort of say, here's a script, go for it. So you get more usage of the model results and data, more people looking at it, it results in good things. Faster feedback to the modeling community, to data providers. You get this, when you start writing code that works with all sorts of different models, you can share it with people, like I was mentioned before, and you can really build a nice library of stuff, of scripts that anyone can use that do lots of cool things. And I think we're going to be seeing a lot more of this in the near future. And really the bottom line is hopefully less time wasted messing around with data and more time spent on science or management or whatever you're doing with this stuff. So I hope you will go take some of these tools and try them out and encourage providers to, if they're not using the standards, you could tell them to give me a call and maybe we can fix them up. And develop tools, like I said, that use the standardized access. So hopefully you found something interesting there. Thank you very much.
Do you have any questions for Rich?
John.
You mentioned you do deal with group 1, group 2. Can you buffer?
Does buffer work with this?
Buffer? Yeah. For point data, satellite.
Yeah, I can't buffer. I don't think, no, buffer doesn't, no, they're not through this service. There's it could be, but there's some other service that gets used for buffer a lot, right? I think that was pre-existing.
Right. But that'd be really useful to a lot of both meteorological and also oceanographic data that a lot of the operational centers have in buffer.
Yeah. And there's other, there's tools. There's a lot of other tools out there, obviously, besides these. There's tools like if you just have a spreadsheet, and you want to upload it somewhere, it'll help you upload it and, add metadata that will make it accessible and things like that. But I've been I was really focused on sort of the multi-dimensional data more and on the big time series data kind of stuff. But and all the problems aren't completely solved. Obviously, I still had to say, we had to go through and figure out where all our variables, what all our different variables were: temperature, temperature, capital T, all that kind of stuff, and basically kind of write a script that mapped those all, and provided the attribute standard of seawater temperature, which is a sort of standard name, to all those data sets. So there's still some work little bit of work to be done to get them obviously into standard form. But I am serious about the offer to help folks if you have a big pile of data that you'd like to try plugging in. I'd be really I'd be happy to talk to you about, and chances are we could write some little script that would maybe add this attribute information, make it accessible without changing your files.
Is there a standard location where you can find out where the other thread servers are and the type of data that they're serving?
That's a great question. So the way it so in the beginning, like for that ICE project, like we went around and installed all these thread servers, and then we made a catalog, like physical, like manual catalog of all those servers, right? And then to find the data, you'd have to go into catalog and go, let's see, which region might this be? Play that game. But with that NC ISO, with that kind of ISO metadata approach, you don't care about that anymore, right? You don't care about maintaining some kind of catalog structure or maintaining a web page that points to a bunch of catalogs. But that's what data.gov is supposed to do. Data.gov so this data, that ISO metadata can actually be flowed into data.gov. Data.gov is not ready yet, but I think it eventually will be. Not too long, it'll be possible to do a query just like the kind I did to my local thing that had harvested 3 catalogs, and instead it'll be pointing to the thing that harvested everything. But now the everything, there's a lot of issues there too about like how often you update your data. If you update, you have real-time data coming in, and the metadata is updating, like stop time is updating every 5 seconds or something, and it only gets harvested by data.gov once a day or something. There's issues, but to find data on threads right now, it's still a little clumsy. But coming soon, I think, will be the ability to not look for threads catalogs, the ability to just do a search and say, give me all the data sets that have OpenDAP URLs, because I know how to deal with those. Yeah.
So this isn't something that I normally think about or do, so
Yeah.
not necessarily my way of thinking, but we do have a researcher here who is producing kind of weather maps for oceanographic conditions, specific if you want to go out and survey. Is this a place I want to go survey based on the oceanographic conditions?
Oh, yeah.
So I think he's using a similar service to go out and grab a small section of data and do the analysis he needs to do and populate a whole grid for large areas and say, all right, this is a good place to go survey based on the oceanography.
Yeah.
But then he's dumping that into a KML, and that's just being put on the web, and you have to download the KML and kind of look at it. So
Yeah.
this is somewhere else he should probably be thinking about going.
Yeah, I mean, I would.
Doing something like this so people then can query what he's producing.
Right. I'd rather see than a KML. I'd rather see a web service like that actually combines those different layers that are being pulled from the different services. And I mean, John's doing some of this with his and Justin, Jason, sorry. And that's what you want to do. You want to come into a web application and be able to dynamically vary. Well, in a lot of cases, you want to be able to dynamically vary the different things you're looking at to find the optimal location or good or bad locations. And there's definitely some of those applications already being built. I saw one the other day that was a web application that was pulling data like this, looking at surface current speeds, wave heights, shipping lanes, and all that kind of stuff. And it was just through a web service again. But the data was coming from these OpenDAP services.
Any other questions for Rich?
All right. Thanks
Thank you
very
very
much.